This data set, it was actually published by the areas team led by Lily Alderson. And actually, it's a data set that if you analyze it from start to end, it's a really cool JWST science data set. It has like a water feature here. It goes in the 3-micron range. It has this beautiful SO2 feature at 4 microns, and then it has this beautiful CO2 feature at around 4.3, 4.4 microns. So there's a lot you can extract from this. So today we'll get you up to the light curves. So, transit spectroscopy, the whole point of transit spectroscopy is that you get transit light curves, and then you measure the transit depth as a function of wavelength. And that gives you the transit spectrum, which is the thing that I'm showing here. Today, we'll only show you up to the light curves. We will not be fitting them. So that it's a set of homework for you. Today, we'll get you all the way from the uncalibrated data all the way to the wavelength dependent light curve, so you can have fun later at home fitting them. All right, so exploring. Let's get to explore these Detector 1 products. I already mentioned to you that there's different stages, and we're going to be stepping first on the first stage of the data reduction, which is Detector calibration. Actually, there's a web page that you can go. If you go to the JWST calibration pipeline, read the docs, so jwst-pipeline.readthedocs.io. Over there, you can actually see a set of steps, the set of steps that define Detector 1. And I grabbed a screenshot and I put it here in the right. And you can see that there's a set of steps for the near infrared, the leftmost columns, and there's a set of steps for the MIRI detector, the rightmost column. Again, same thing that I mentioned before. The near infrared detectors, like the ones from NIRIS, NIRCam, and NIRSpec, are different beasts too. The MIRI detectors, they follow also different steps. Sometimes they have steps in common, like saturation, for instance. Both of them for time series observations. Both of them do saturation, but the order and the actual steps that they follow are a bit different. So we're going to follow the one in the near infrared. And again, Detector 1 deals with everything detector level. And these are key actually to study and understand how to reach these desired signal to noise levels with real data. One thing that we've learned and understood out of this data is that having a proper detector calibration actually kind of ensures that you get the best signal to noise out of your data. That's why it's so important, and that's why we wanted to give you a little tour through Detector 1. So that's exactly what this notebook does. And actually, if you go through here in section 3, you go through all the steps, they all kind of match one of these steps of the pipeline. Let me go directly to the notebook so you can see what we'll be dealing with. And in this notebook, you can actually see that the first part, this section 2, actually handles everything that has to do with downloading the data. And we're going to go into that right now. So you, of course, will not be downloading the data. I already run the entire notebook, but you can run it as we go. The very first cell actually just ingests, just initializes all the libraries that we will use. As you note, we're not using a lot of libraries, just some particularly from the JWST calibration pipeline, we will be using the JWST library. We're going to be importing the data models function / object. We're going to deal a lot with data models. I'm going to get you into that in a minute. But this thing, this is like JWST Data Analysis 101 is getting these data models for you to play with. And we're importing the JWST calibration, CalWeb Detector 1, which is the one that's going to, do all the magic on our data. Very important, this second cell that I have here in which you print the JWST version. Always do this and always try to report that in your own paper so we all know how you did your analysis. The pipeline is constantly evolving, so it's important that you keep track of which version of the pipeline we'll be using. We'll be using here 1.12.5. Right, so the second section of the notebook, it's actually downloading the data. We'll go very quick through this because really we are not downloading the data here because the data is already set in your environment. So that's why I've set this to false. But if you're running this, if you download the notebook and you want to run it locally, if you turn this to true, it will use Astro Query to actually download your data. And this is a very handy set of functions because you can download any data set you want. Here we are downloading the WAS39 data set from proposal ID 1366, which is the ERS one. We're using NIRSpec slit and the G395H and F290LP filter. So, you can do all your combinations for any data set you want, and you will get your data in this. When you download data, in particular here, we are downloading uncalibrated products. This uncal, this cell number 4 here, goes into uncal data sets. So that's actually data that has not been gone through the JWST calibration pipeline. It does have its own headers and so on, but on top of that, there's nothing else done to the data. And you will notice something very interesting out of this data set. Two things. So the first one is that it seems that there's two types of data that you download. There's a set of data that actually it's what we call the target acquisition. I'm going to go in a minute into what exactly that is. And there's your science data. And your science data set, you will notice that in the file names, it has sec001, sec002, and sec003. That is the fact that when we download the data from JWST to the ground, the data set is typically for TSOs that are too large to pass through the pipeline. I mean, you could, but you will use a lot of memory. And what we do is that we cut that data basically in little slices that we call segments. And then that allows us to do, data reduction in parallel, or that allows you to do, serialized data reduction with less memory requirements, basically. So that's why the data is segmented. But if you join this data in like a big array, then you will have the entire exposure as we observed it from JWST. The other detail that you'll note in the file names, as you are noticing the file names have a lot of information, is this NRS1 and NRS2. This data set that we're using actually uses 2 detectors to get the data. And each of these 2 detectors observes a different wavelength range, one from 3 to 4 microns, which is NRS1. And the NRS2 detectors goes all the way from 4 microns to 5 microns. We're going to see an image in a minute on that. So we'll get much more clear. But the main point is that, remember, data is segmented typically for TSOs. There's data sets that have like 40 segments. And there's data from different detectors in this particular data set. Okay, and that's your science data, but then you also have target acquisition. Taking your target acquisition frames is very important because that lets you know if your observation went correctly or not. Target acquisition is done targets to basically center the position of the instrument into your target. And typically it goes to your star, or sometimes it goes to a companion star that is nearby. And again, it's used to center the instrument center the star in the detector. And so we're given here in this notebook in cells 7, 8, and 9, like a little plotting of this TA. And you can see a little blob of light here. That's actually the star. And you can note that it's kind of offset from the target. This was not a perfect TA. It was not in the center. Typically, TAs that are done now routinely, they all fall in the center, but this one is slightly offset. That's okay. That was not a problem for this particular data set, but it's something that you should always check. For instance, if you go and check the target acquisition image and there's nothing, and that's a red flag, right? That should make you a bit worried, because it means that the target was not around and then it was not centered. And probably when you go and look your spectrum, the spectrum probably will not be there. That's bad. But in this case, the TA is slightly offset, but it's there, so it's fine. And so that's what we do next in section 2.3, in which we go and take a look at actually the actual science data. One thing that I missed that we did with the TA data is that we loaded with these data models. You remember I told you that it was like a very key thing to keep an eye on, that you were using data models a lot. So data models, it's actually, as the name suggests, a data model for JWST science that was built within the JWST calibration pipeline to read in your data. So instead of reading it because these are all FITS files, right? So you might go to astropy.io, import FITS, right? You might want to read it like that. But there's many advantages of reading the data instead through data models, because they allow you to do a lot of neat stuff. For instance, here, I'm loading the data, the uncalibrated data for NRS1 and NRS2 on 2 arrays. So note that I'm just doing 2 arrays and 2 lists, 2 Python lists, each of them which has 3 elements, and each element is one of these data models objects. So I'm reading them as ramp models. So data models have different types of models, ramp models. You can also do simply open, and then that it will kind of automatically try to check which kind of data this is. But in this case, we know these are ramps because it's the uncalibrated data, and we go and read the uncal data with ramp model. You'll be wondering, Nestor, why use data models and not something else? Well, check this out. Once I read in these on-call data into these data models, I can just play with the data models as we go. So for instance, in this case for NRS1, I read the first segment of data first, the second segment of data next, and then the third segment of data. And then I repeated the same for NRS2. First segment, second segment, third segment. And down here, I can just call the first segment of data, because this is a list, a Python list. I just call the first element, which is, again, the first segment of data, which is this one. And then I can do, for instance, a search on the header, on the metadata that the data model has. So you know how when you read like a FITS file and you check through the headers, it's kind of complicated because you don't know what kind of headers you have, or if the date of the observation, where exactly it is, and you have to go down through it, and it's kind of a pain. Well, data models actually have this very handy dandy function, which is called search, in which you can search keywords, and then automatically this thing will print you keywords that match the string that you're passing. In this case, I'm passing the string date. So I'm trying to search is there any dates in my data that I can look up in the metadata? And indeed, there's tons of dates. So there's this first date in this meta date, and there's this date of the creation of this file, which might be interesting. I'm printing it down here, but it might not be that interesting. But the one that is interesting, for instance, is the observation date, for instance, here, which is this tells you when it was observed, when the data was began to be observed, and when it ended. So you can extract all this kind of information using this data model function search. If you're not interested in that, and for instance, you want to search for the PI, that information should be on the metadata and the headers of your data. And actually, right away, bam, this throws me, that the PI name is Natalie Battaglia, which makes sense. She was the PI. She is the PI of the ARS program. And of course, you can read that directly if you know the metadata link. You can just read it here directly from the data model. So data models are extremely handy. And one of the things, of course, that you can do is read the actual data, right? And here I'm reading up the data. So this .data gives you back the array, like an array of data. And here I'm plotting the shape. So the shape is, again, once you are familiar with the RAM sampling, it's kind of sort of intuitive. The first dimension is integrations of your data. The next one is groups. You remember that you do this the RAM sampling on each integration. And then the last two dimensions are just pixel coordinates, which is the size of the subarray, the detector subarray that we're using. So I just went ahead here and I just choose like a random integration 10, and I choose like a random group, which was the last group. And I plotted the NRS1 uncalibrated data and the NRS2 uncalibrated data. And you might see right away that that's already a handful. Like, look, I'm just pointing it here again. As I was explaining to you before, the NRS1 data contains all the data from 3 to 4 microns, and NRS2 all the way from 4 to 5 microns. But look at that background. There's a lot of stuff happening in the background. Most of that stuff, it's actually detector things. So it's everything. Most of it is just detector. And that's why Detector 1 is so important, because it goes from this to a final, very pristine image that has all these detector effects like calibrated. Just removes them from your data. So let's go to the first step of the pipeline. Right now, we have not touched the pipeline, and now we're going to deep dive into it. The very first step of the pipeline, well, actually, the very first step is this group scale, which is never of use to us. So you don't need to worry about that. But the actual first step that it's of use to us is this DQ init step in the Detector 1 stage. And this DQ init stands, in my mind, as the data quality initialization, basically. Or, if you want to think it like that, the bad pixel mask. So you have for all your detectors, the instrument teams have looked at every pixel, and they've studied the lives of every pixel and decided, like, this pixel it behaves a bit weirdly, so we're gonna mark it and we're gonna flag it. And all those flags are in what we colloquially know as a bad pixel mask. And the DQ init, what it does is that it fetches this bad pixel mask from a server called CRDS, and then it attaches that to your data. So it gets stitched to your data, so you can read it and figure out what pixel, if your favorite pixel has any flag associated to it. So let's just do that in the meantime. So this is in section 3 in the first 3.1 section. You can run the DQ in it. I'm running it here just in one segment of data for now to initialize the thing. And what this thing does, is that it initializes another attribute. So you remember that we were just exploring the data attribute of your data model. This attaches a new attribute to your data, which it's called the pixel DQ. And I call this like checking special pixels. And we're going to go to saturated pixels in a minute. But I think this discussion it's important to put here. So there's two kind of attributes that you want to pay a lot of attention to. There's the pixel DQ, which is pixel data quality, and there's the group DQ, which is the group data quality. The pixel data quality is the one that we're dealing with right now with the DQ init step. And the dimensions of this pixel DQ are the same as your subarray of your detector, which in this case is 32 times 248. And this defines, again, the pixel status for all groups and all integrations, because sometimes a pixel is called do not use, and the pixel does not get used for the rest of your exposure. And so it's something that is defined for your pixel forever, basically, right? So you just stick with that flag. The group data quality that we have not initialized yet, and I'm going to go into that in a minute, that one defines like pixel flags for each group and each integration. For instance, if you have like a cosmic ray, for instance, then the group data quality will interact with that and will flag that pixel at a given group in a given integration. Or if your pixel is saturated, for instance, then that will get done there. So these two things that you want to pay attention to, the pixel data quality and the group data quality, get initialized by different steps. Pixel data quality is initialized by this DQ init step that we just run. And the group data quality is going to get initialized by the saturation step and the jump step that I'm going to be explaining in a minute. Let's get back to the notebook. I'm going to go a bit quickly. So in cell 21, what we do is to just plot where all the non-zero data qualities, pixel data qualities are. You might be wondering, well, okay, this is like an array, right? So if I print here the pixel data quality, you will notice that this is an array of values, and each pixel has its value. You might be wondering, well, what does those values mean, right? That's a number. I don't know numbers. Well, if you click here in the notebook, I actually put a link to what value corresponds to what kind of fat pixel, basically. So there's do not use pixels, there's saturated pixels, there's like persistent pixels, and so on. We will not go into detail on what each of these means. But basically, every pixel that is non-zero in the pixel DQ means that something special is happening with that pixel. And that's exactly what I'm plotting. So for instance, if I go to a random pixel, chances are that I'll hit a good pixel. So I'm going to choose, I don't know, pixel 100 to 100. And, pixel DQ over here. Okay. So I'll do, sorry, I meant, of course, 100 is above the limits. So I'm going to do 10, 100. Okay. That one is a good pixel, has a value of 0. So here I'm plotting all the pixels that have values of non-zero. That are kind of dispersed everywhere. So that's fine. Now, you might be wondering, well, Nestor, this is all fun, but I don't want to go and be looking at these numbers and trying to go back into this big table and figuring out what this pixel means, right? Well, do not fear. The whole point is that we have functions for you that are useful to actually figure that out. And in particular, you remember these data models import that we did at the very beginning, and I told you that's very important. It is very important now again. There's actually this function that it's called data models.dqflags to mnemonics, that if you ingest a value, like the values that I was just mentioning before, and you ingest a mnemonic map, which actually the data models port itself has, and just copy paste this same thing here in cell 23. If you pass a value here, it will spit out what that value means with a human readable string, right? And actually in cell 24, I do a for loop through all these pixels to figure out how many pixels of different marks they are, right? A total tally of bad pixels, if you will. So there's 256 reference pixels. I'm gonna go into what a reference pixel actually is in a minute. 251 do not use, and so on. So there's only a handful. It's a very tiny amount of special pixels that is in the entire subarray, which is great. Right? And then in cell 25, I just attach this bad pixel mask to all my segments of data to both my detectors. And that's it. That's with the DQ init step. It's very straightforward. Attach bad pixel mask to my data step. Right. So the next step, now it starts getting very interesting. The next step is the saturation. And the saturation step is very special because it actually flags saturated pixels. And that's the next step on the detector one, after the DQ unit step. And flagging saturated pixels, in principle, is actually pretty easy. So you have your detector, right? And you have your off-the-ramp samples. And here I'm, this is just a plot of one pixel that I made up. And if in a given group, your counts go above what we call the saturation limit, which, by the way, has been investigated by the instrument teams. This is typically a limit above which the nonlinearity solution starts working pretty badly. What is this nonlinearity solution? I'm going to explain it in a minute, so keep that in mind. If a pixel goes above this saturation limit that the instrument teams have figured out, then we flag that pixel as saturated. Now, interesting thing is that not only the saturated pixel gets flagged, the pixels around it also get flagged in the latest version of the pipeline that actually we are using. You might be wondering, why, Nestor? Why would I flag the pixels around it? Well, we have seen that when a pixel hits saturation, a lot of the charge that the pixel is accumulating goes to nearby pixels. There's some charge spilling, charge migration, if you want to call it like that. And then that messes up also the off-the-ramp sample shape of the pixels around it. You typically would expect for this to be aligned, and I'm going to show you that mostly that's the case. But if you have a saturated pixel and you look at the pixels around it, all of them deviate very significantly from a line, and then that's why they get flagged too. You can actually modify that behavior in the pipeline if you want. I'm gonna that's in the notebook itself. I'm gonna teach you in a minute how to do that, but this is a very important point to understand on how the saturation step works. So you can just run the saturation step. I'm gonna go pretty quickly through it because this is already in the notebook itself, and you can read all about it because we went into a lot of detail. The interesting thing is that remember this data model.dq flags to mnemonics, you can also count the number of saturated pixels. I wrote like a little function here that just goes in a particular integration in a particular group. It just checks how many saturated pixels there are. And in this case, for integration 10 and group, the last group, there's only like 27 out of all the pixels, like 0.04% pixels are saturated. So just a small fraction of pixels are saturated. And just here's like a little plot showcasing one of those saturated pixels. So counts are in red for that pixel, so different as a group number. And I'm also plotting the group data quality. Group data quality of 2 means saturated. You can read that in this little handy dandy table. You remember here, like 2 is saturated. So you see how this poor pixel, it was hanging around 10,000 counts, but around group 13, bam, something hit it, probably a cosmic ray, just went up and went above this saturation limit, and then it gets flagged as saturated. I have a section here that you can read later on how you can figure out what the saturation limit for each pixel is. The bottom line is that all of this is in what we call a reference file. In this case, you can read from the data model itself. Remember, I told you the data models are really, really handy really handy objects, sorry. You can read from the data models themselves what reference file was used to reduce your data. In this case, is this saturation file 0028, and you can actually read that file and plot what the saturation limit is for your favorite pixel, and that's exactly what I do here. And you see how the pipeline is doing what it's supposed to do, right? The pixel went above this limit, which is the dashed red line, and it got marked as saturated. So you can explore this at any level of detail you want, basically. And that's what this notebook teaches you how to do. So saturation step, again, it's very simple. And all this information, as you remember from the discussion before, information about if the pixel is saturated or not gets printed in this group DQ attribute of your data product, right? This group DQ. Remember that bad pixels get in the pixel DQ, and saturation, for instance, gets imprinted, and flagged in the group data quality, group DQ attribute of your data. And then in these following cells, I just change slightly the saturation limit. I will not go into detail into that. It's not extremely important. But if you're interested in knowing how to change the saturation limits, you can read the notebook in detail later. So here, cell 42, what I do is that I apply the saturation step to every data set. to both detectors and all the segments. All right. So far we have not really touched the data, right? We have gone only through flying pixels. So we run through this DQ init step and the saturation step, and both of them, they just flag pixels, but we have not touched the data yet. Now we enter a step which actually does some detector calibration per se on the actual data. The very first one that we do in near-infrared detectors is this super bias step. And the super bias step, what it does is that removes detector pedestal. It's sort of constant on every group, every integration. That it's set by from when the detector was made. So this is something that has been measured on Sky, and the instrument teams are constantly updating this super bias and uploading them as reference files too. And what this does is that this fetches this super bias from this server. It applies it to your data and removes that, and then your data looks much prettier. How much prettier? I'm going to show you in a second. So section 3.3 goes to removing these detector level effects, and 3.3.1 goes to using the super bias step. Here I just applied the super bias step to my data that has already been passed through the saturation step. And here's just like a before and after, right, of this super bias step. Sorry, I just did like a control minus to show you the entire thing. So before the super bias step, you see in the top, it's kind of difficult to see the actual background because everything's kind of mixed up because there's a lot of variation, fluctuation in the data. But then after the super bias step, know that how the background looks much better. Like these wings of brightness here, they just go away because those are by the super bias as well. If you don't believe me from this 2D image, here I have like a little cut. I just did a cut. I can't remember which pixel was this column 1500. So I just did a cut like here, this column. And then what I'm gonna plot is like the before and after. Before is blue, and you see very high frequency variations. All of those are just most of those are just super biased. And after the super bias step, boom, they're all gone. It's much smoother, much nicer, which is great, and it's very satisfying to see. All right, so and step basically has to do, and this is section 3.3.2. So okay, super bias step is as simple as removing this pedestal, and that's it. And you do a very good job. But then there's also, so the pedestal is assumed to be constant across groups and integration. However, near-infrared detectors are complex things, and they actually might have detector effects that are dependent on the group that you observe the detector. I'm going to show you in a minute what that looks like, but there's some group level detector effects that you need to remove. And this is where the reference pixel step gets into play. So first of all, I'm speaking about reference pixels for a while now, and I haven't explained what are reference. I'm going to explain to you what a reference pixel actually is. So, and that's the next step, the ref pix step. This removes group level effect. On board JWST, the full detectors, they all have what we call reference pixels. And reference pixels are pixels that are insensitive to light. Or I think a very precise way, a more precise way of telling that is that their capability to read counts from photons has been like turned off. So the near-infrared detectors have reference pixels on the edges. It's like a 4-pixel wide band around the detector. And the infrared detectors on MIRI only have on the corner. Interesting thing, however, is that when you are doing time series observations, you want to read with very, very fast cadence. And reading the entire detector takes a lot of time. Also, it will saturate the detector very, very quickly. So what we do is that we read in subarrays. We read in like portions of the detectors. And that's a double-edged sword. It's great because you can read faster and brighter objects. But the counter side is that some of those subarrays don't have reference pixels. For instance, the MIRI slitless prism LRS subarray does have typically reference pixels. NearSpec SUV 512, the one that people using NearSpec Prism, for instance, use typically, that one doesn't have reference pixels. But the one that we're using, SUV 2048, for this data set, it does have reference pixels and has reference pixels on the edges. So these ones are actually used to remove this detector level effect because the whole point of having pixels that are insensitive to light, photons, is that they map anything that's happening on the detector at the same time that you're observing, which is great, right? And then there's very neat algorithms already implemented in the GWSD pipeline that allows you to take care of that. So here I plotted a linear function in cell 47 and 48 to indicate where these 4 columns are, like in the very edge, these little white stripes here. Those are where the reference pixels are. And in particular, because it's in the edges, you can only take care of like row-to-row effects. And in particular, for near spec, there's this odd-even effect, it's called, in which all the odd rows and all the even rows, they're like kind of offset in flux. I'm going to show you in a second what that looks like. So here I'm plotting all the odd rows for a given integration and a given group. I think this is integration number 10, and this is the last group of integration number 10 of my data that has been supervised subtracted. And you can see that there's a slight offset between the blue, which is the odd rows, and the even rows, especially kind of in the background. If you run through the reference pixel step, which I do in cell 50, then you actually see that that's no more. You see that the red ones and the blue ones are side by side, they're in the same level. So I'm going to show you again the before, they're a little offset. The blue is a little bit higher, and after, the blue is like at the same level as the red one. You can see it there, you can see it in a 2D image too. So the top one here is before the reference pixel step, and I don't know if you can see that, but there's like these different bands. So look at this even, I think it's the even, yeah. The even pixel, the even row. There's a row here, even row here, even row here, and it's like some banding that then disappears when you apply the reference pixel step, because that's exactly what this step does. It removes this row-to-row effect. Problem is, however, that it doesn't take care of column detector effects. So there's some banding. I don't know if you can see here, but in the vertical direction in the columns, there is some banding that changes between integration to integration and between groups too. We're going to take care of that in a minute on our own. But the reference pixel in this case, the reference pixel step, again, is taking care of only effects that cover their rows. But again, there's also effects that happen in the columns that this reference pixel step is not taking care of because where the reference pixels are located. All right, let's keep going. Next step is the linearity step. And I spoke about the linearity before, and it was kind of fast as you moved through that. But the next step is also very important, which corrects for nonlinearity. Nonlinearity is this effect that pixels kind of as they get more and more electrons blown up from the little photons that hit them, they get kind of less efficient at counting more photons that come in. And then instead of keep reading with more photons, they kind of go down a little bit. They're not as efficient with high number of counts. And I'm going to show you, I show here in the notebook directly that you can see that with your data. So here's, for instance, without one of the ramp samples for pixel 11,2000 for integration 10, I'm plotting all the groups, all the 70 groups. And, you know, it goes as expected. Those are the black points, the white points. They go as expected. If I feed a little line with just the very first few groups, and then I try to predict how much counts it should read at the end, you see how the white points go down that line? That means that it's non-linear, right? It's getting worse and worse at reading counts at the large number of counts. If I apply the linearity correction, which I do here, and I plot the same thing, notice what happens. Thing gets back into line, right? Which is great. It's very pleasing to see. This linearity correction, works. Now, ourselves, maybe it works at the big level, like you can see it by eye, but maybe if I do a huge close-up here, maybe I see like a slight deviation. So the whole point is that if you have a perfect ramp sample, this thing should follow a line, right? And if you take any difference between two subsequent groups, the difference between two subsequent groups should be the same. If it's not, then nonlinearity is doing its thing. So what you can do, for instance, is take the difference between the last two groups and say you get, 1,000 counts. And then you repeat the same exercise with the first two groups. The last two groups and the first two groups, you take the difference, and the difference should be the same if this thing were linear, right? So then what you do is you take the ratio between those two. 1 if linear. I mean, if it deviates from 1, then something's going on. Well, we did that exact same thing in this notebook. And when you don't have a linearity correction, what we're doing here, we're plotting the last group difference over the first group difference, the same thing that I told you just now in the y-axis. On the x-axis, I'm plotting the fluence on the last group. So, if you do this up the ramp sample for this pixel, the fluence in the last group will be this one, like around, 23,000 counts. That basically measures, how much brightness you had in your poor pixel. And pixels that are more to the right are more heavily being bombarded by photons, right? So without linearity correction, you see that this thing does not match as one, right? And particular for high counts, it goes like very low, which is the same effect that we were observing here, right? The counts are going below what you observe in the very first few groups. And that's exactly what's going on here. Now, when you correct for linearity, look at this. This thing gets around 1, which is beautiful. Now, this thing is not perfect, however. You can observe how at very high counts, on average, they are slightly below 1. There's some hypotheses on why that is happening. It might be, the nonlinearity correction not being perfect on one end, but also you remember I told you about this charge migration before. That charge migration starts kicking in very early, like around 10,000 counts or so. There's a paper by Paul Goodfruge a couple of weeks ago on the archive studying this in NIRIS, which is also applicable for this NIRIS data, I guess, in which you can see that that charge migration might be happening too. And this is just an hypothesis on this particular data set, because with this plot, we cannot do a statement about that. It might be. So we just plot here, just discuss a little bit why this might be happening. But from here, nonlinearity correction to this with linearity correction, huge improvement. And actually, as we're going to showcase in a minute, the data looks pretty nice. So what we do here in cell 66 is just apply the linearity correction to everything. The next step in the JWST pipeline, after the linearity step, is the dark current step. And the dark current, as you see here, comes after the linearity. And dark current just corrects for the dark current, as the name implies, right? So what happens is that as you read up the ramp, the detectors themselves have some electrons that are, wandering around, and they get stuck just because of detector temperature, basically. The temperatures of JWST detectors are very low, so the dark current is actually super low. But still, you might want to check your own data for impacts of dark current. I'm not going to discuss that in a lot. There's a lot of text here that discusses, how you can check that, how you can check that on your data set. But the main message that we want to send with the dark current step is that we will really encourage you to do a reduction without the dark current, with the dark current, and see if your results change. For most of the TSO data sets, it doesn't matter very much. But there might be some data sets out there, especially for targets that are very faint, in which this might matter more. So you should always want to keep this in mind. Here we just apply the dark current step, and we do some checks on how large the dark current is on this particular data set. Not very large, as you might expect, but we just run it through the pipeline. One thing that it's not currently on the JWST pipeline is correction for what we call 1/F noise. 1/F noise is a kind of noise that appears on each group, in each individual group, and I'm going to show you in a second how that looks like. It's this sort of banding that I was mentioning to you before, right? So if you look at the 10 integration and the different groups, I'm plotting really group differences, but step that aside, just believe me that this happens also in each group. You see that this banding on the background kind of changes. So from this one in the top, from this one in the bottom, you don't see the same structure. Then this one changes again, this one changes again, and all this banding kind of changes places. The reason why this happens, I'm going to go through it kind of quickly. So it's this banding. And the reason has to do with how JWST detectors are actually read. Pixels in JWST detectors are read sequentially by a mechanism, an electronic mechanism, which is attached to what we call the ASICs. And the ASICs, what they do is that they go reading each pixel individually every 10 microseconds. They go read the next pixel and next pixel and so on until they get to the end. Then there's a wait time. We tell this thing to wait for 120 microseconds, not because they're lazy, it's because we want to synchronize the detectors. And then we go to the next column. Again, we read 10 microseconds, 10 microseconds, and then we go to the end. We wait 120 microseconds and so on. So we read everything sequentially until the last detector column. Until the end, we add a little pad time, so one little bit of extra time so everything gets synchronized. And that's what you typically understand as the frame time. That's the frame time that you typically read in the JWebSD documentation. In the meantime, the reading mechanism has its own noise because no electronics is noise free, and that includes the readout electronics on board JWebSD. In particular, the readout electronics for the near-infrared detectors, they have this underlying noise that it's 1/f actually time series, and you read this noise together with your counts too. And because there's a wait time and the noise keeps happening, there's a portion of that noise that you don't see because of this wait. And then you keep reading, and this noise gets added to your data. It's called 1/f noise because if you manage to see this noise time series and you plot the power spectral density, it has this beautiful shape which is 1/f, as frequency. And the symptom, it's actually this band. So here we actually go and do a couple sections, subsections on how to remove that from your data. It's actually pretty simple what we do here. What we do is that we just go through the spectra and we trace the spectra. So we do a little algorithm here to just find kind of the centroids of each part of the spectrum here. And then we just feed a polynomial through it, and you have like a very, very simple spectral trace that then you use to mask pixels. You mask all the pixels that are illuminated, which are the ones in the center of the trace, and then you just drop them. And then you use the pixels in black here, which are the background pixels, to figure out these column by column noise. So what we do is that we take the median on each column of all the background pixels, and we remove that from the detector. And you can see the effect here, before that correction, you don't do anything, and after that correction, a lot of the banding is kind of gone, which is great. We correct for that, and if you want to know details on how to correct that, you can check the notebook, but it's pretty straightforward. The second to last step that goes through is the jump step. As the name suggests, the jump step, it's actually detects jumps on your the ramp sample, and that's the second to last, and the ones that we'll explain in detail before moving on. The jump step, what it does is that it tries to detect little jumps that might happen by these cosmic rays, this CR. And when cosmic ray hits a given pixel, then that pixel count might jump, kind of abruptly. And then if it's not saturated, the up the ramp sampling will keep going. So you want to use those samples that come afterwards and the ones that came before. So detecting that jump is very, very, very important. The way the detection algorithm works is that it takes the difference influence between all two-step sequence groups, so 2 minus 1, 3 minus 2, and then takes the median of all those, that they should be more or less constant. And after that, you just kind of do a 5 sigma rejection of any group difference that went above or below that median level between the groups. It's as simple as that. Now, in the notebook, we do there's one example here, a real case of a jump here that gets detected and it gets attached to the group data quality. And you can actually see it in the 2D images. So here's an inset of the spectra. So you don't see anything in group 15, integration 66. But the same group in integration 67, you see this huge jump here, which is this one that you're seeing here. It gets detected and it gets flagged with the jump detection step. There's a little blue note here that I wanted to pay attention, point you to, in which you can modify some parameters of the jump detection. In particular, the rejection threshold, to know how aggressive the algorithm is at removing and detecting these jumps. It's very important. It's something that you might want to check with your data set. The default value is like a 4 sigma detection rejection threshold, but there's some data sets in which a value of 10 or 15 might be more appropriate. So always in your data, try different rejection thresholds for your jump detection and see how it behaves on your own data set, right? How the light curves at the end look like, for instance. And that basically sets the core of what the Detector 1 step does. The very final step is the ramp fitting step. So what this thing does, it seems pretty simple. It just fits slopes. So what it does is that it goes to your group level data. I'm going to go here in this section 3.8 that sets the ramp fitting. It gets your data and tries to fit a slope to your data. So what you get after this step is not a ramp, but this slope. So you get some counts per second that get attached, and then a new data product is generated. What that data product of the slopes of each pixel at a given integration, we call them the rates per integration. Rates because you're measuring a rate, right? How much flux you're getting as a function of time. And per integration because at each integration, for each pixel, at each integration, you get a different rate. And that's actually what most people use for their TSO analysis, particular transit in exoplanet peaks. One word of caution, you're thinking, well, this is measuring slopes, right? How hard can it be to fit slopes? Well, you have to keep in mind that off-the-ramp sampling is not a simple least squares fit. The reason for that is that off-the-ramp sampling is a Poisson process with error. So what happens is that, in your first group, you read electrons, which is the electrons that come because of your photon that is hitting your pixel, plus some noise. But then in the next group, you have those same electrons on top of the new electrons that are coming from the next set of photons, plus a different instance of the noise. And the next group, you do the same, and you see how the process goes in that different groups or different frames are correlated because they're using the same number of electrons. And you have to account for that correlation in your fit to your slopes, otherwise you severely underestimate the error bar on your slope. The JWSD pipeline actually does this pretty well. It has a nice algorithm embedded into it and accounts for this correlation. And then you can get these rates per integration directly with the pipeline. What we do next in the notebook is that we just do this. We just run fitting for all the segments for both of the detectors. And then we just craft like a crude white light curve by just adding up all the flux detectors for all the integrations. And we plot them here. And you can actually see right off this crude thing, these white light curves, with of course a lot of outliers.